So hello everyone, and thanks for joining us. As many of you may know, I'm Arndís Bergsdóttir and I organize these ROCS lecture series. And today I have the great pleasure of introducing ROCS collaborator Árni Einarsson, who will speak to us about timescales of wildlife studies at a biodiversity hotspot. He has a PhD in ecology and has been studying various aspects of the ecology of Lake Myvatn for half a century. And that includes waterbirds, fish, invertebrates, and algae, and also sedimentary records of the biota. He is currently a guest professor at the University of Iceland and the former director of the Myvatn Research Station. So without further delay, Árni, once again, welcome, and I'm delighted to have you with us. And I will now give the floor to you.
Thank you very much, and thank you for inviting me. Well, as Arti says, Lake Myvatn is now part of the ROCS project, and this is a lake where I've spent almost all my life studying, at least for the last 50 years. And I'm a bird person, as Arti said, but the tragedy of my life is that I've become more of a microbiologist in the last few years. So my studies have drifted from birds down the food web of the lake and down to the algae and now to the bacteria of the lake. So that's how it goes. Lake Myvatn, I guess you know about it already. Now I'm just learning how to shift the slides. Lake Myvatn is in North Iceland, and it's a volcanic lake. What you see is the post-glacial lava fields in Iceland, colored in red, and Myvatn is on top of one of them. So it's like all lakes in Iceland, a post-glacial lake, but also very recent. It's only just about 2,000 years old. And the whole water catchment, it has a large water catchment, and it's completely covered with lava fields and sand and this kind of landscape with hardly any running water. All the precipitation is going as groundwater towards Lake Myvatn. And this groundwater is a source of phosphate, which is fertilizing the lake. It's the most important aspect of the nutrient rich, or the richness of the biota of Myvatn. So that's a basis. It's a moderately large lake. It's not very large, but it's not small either. It's a shallow lake, between 2 and 3 meters in depth. It's surrounded by lava. It has all sorts of lava or volcanic features, including the pseudocraters that you see here as islands in the lake, and a lot of depths, which are the kind of signature organisms of the lake. There's a lot of water running through the system, and this is the outlet. It's quite a big river Laxá. And the surroundings in the middle of this volcanic scenery, you can see a lot of green color. It's all linked to the fertility of the lake. This phosphate that's characterizing this groundwater. We have been able to determine the age of the lake with radiocarbon, and unfortunately we get 2 dates because there's a kink in the calibration curve of C14, so we get 2 different dates. One is 200 BC and the other one is about 330 BC. It's the time of Archimedes on one hand and the time of Alexander the Great. In the other case, and if you use tephrochronology to date the lake, you derive at the older date. So 330 BC is the kind of official age of the lake or date of the lake birth. So it's a very young lake. The Myvatn Research Station was established in 1974, 50 years ago. And I started to work there in 1975. And when it was established, the monitoring program of the lake biota was started by looking at the ducks, counting ducks. In 1977, we started counting the insects, and we have been adding other things as well, like the fish species, the crustaceans, the plants, and almost everything you can dream of. It was planned as a 100-year project. It was done so deliberately in order to so we could select methods that would be not be outdated. We're using simple methods for monitoring, simple and cheap methods that would survive financial crisis. And so it was designed so that one person could carry it out, whatever. And over the years, we have been gathering information. There's been a lot of research projects going on in collaboration with a lot of people all over the world. Myvatn is by now quite famous in the field of linology or freshwater ecology. It's one of the best studied freshwater lakes in the world. So this is the system. Ducks are the characteristic animals. We have 15 species of ducks, which is a lot. We have, on the other hand, we have only 3 species of fish, which is very, very few. Only those 3, the brown trout, the Arctic char, and the stickleback. And we have invertebrates that those vertebrates are using as food. The microcrustaceans, both planktonic ones and benthic, and all the midges. The midge larvae are living in the lake. And then we have the phytobenthos, the macrophytes, the plants living on the bottom of the lake, and the microalgae as well, both planktonic and benthic. There's a lot of species of insects and crustaceans and plants and diatoms. Just the diatoms are about 100 species. So we can call it a biodiversity well, it's a we can say that the biodiversity is very high in relation to the latitude. Fishing has been very important all the time. The area was settled 1100 years ago. At the time when Iceland was settled, it was actually one of the first areas that were settled in Iceland, or Myvatn was settled almost immediately with no delay, even though it's quite far away from the coast. People have been fishing. It has been a very important part of the livelihood, fishing using gill nets and line fishing and with seine nets in the winter. And this is the main fish, the Arctic char, here on the breeding ground in the early winter. And so that's where I'm going to begin my story. When we came in 1975 to start the monitoring and the research on the lake, we met the old men who had been fishing there for their whole lifetime, and they had a fishing record, and this is the fishing record that they had. The catch is on the left, on the vertical axis, in tens of thousands of fish. So they were catching about 3,000 fish annually, very variable, but pretty stable. So everybody was quite happy with that, because this was a sign that everything was good. There was stability. We had all heard about the balance of nature, which was fashionable at the time. And so Myvatn was taken as a prime example of a balance of nature, where people and nature were in harmony. And then we started working there, and we started observing a major decline in everything. It was not our fault, we thought, but there was something that was changing very, very rapidly. It took a while. It took a long time to realize that this was something that was becoming a long-term thing. And this diagram ends in 2000, and it's still, the fish catch is still close to zero. It's regulated now. The fish is almost protected from fishing. Just some fishing is allowed in order to keep people happy. They can go out and fish for their dinner, and that's it. So the catch is almost zero, and it took only 20, 30 years to reach this state. And we started questioning ourselves about this balance of nature, and we started wondering if there was overfishing, or if somebody was doing something wrong. The farmers didn't start recording the fishery in the 1930s, but they started already at the turn of the century, because they started a fishing society, and they wanted to try out some management practice. So they kept a record of the fishing. And when you look back at it, this is what you see. So around 1920, there was a huge peak in the fishing. which is the maximum of the 20th century. So when you look this far back, you get a completely different picture of what was actually going on. You can see it as a downward trend. You can also see it as a single peak, some event in the history of the lake, and then some period of stability, and then this steady decline and near extinction of the fish. So this is a lesson. We had been busy studying the lake during this period, and one thing we did was to collect the fish from or data from the fishing nets, and also the ducks that were caught by the fishermen. There were thousands of ducks being killed by the fishery, and we collected them as much as we could, and we dissected them to see what they had been feeding on. Also, the farmers were not only keeping a record of the fishery, but they were also collecting eggs from the ducks, especially in the former half of the century. And they kept a record of the duck eggs, not only the total of eggs, but divided between the different species. The reason they did that was that they were farmers going from many households together to the nesting colonies of the ducks and collecting all the eggs they could. And when they got home, they had to divide the harvest between themselves, and the different species had were laying eggs of different value to the farmers. So because they were different size and they were different taste also. So this is part of the record. You can see that some of the species were not changing very much in their egg laying between 1900 and 1957 or so. But there is this red curve. There's a duck. There were actually two ducks that were following this red curve approximately, with his peak in around 1918. And when you look at it, it is suspicious that's in the Arctic jar around 1922, a little bit later, just 3 or 4 years later than the ducks, which is normal if you take into consideration that the fish need time to grow to the size when you can catch them. There's a little bit of a time lag between ducks and char, ducks and the fish. So because we had been looking into the stomachs of the ducks, we knew that there are 2 of the ducks that are feeding on different food than all the other ducks. They're feeding on these microcrustaceans we call Eurycercus, and this is also the favorite food of the Arctic char. So there are 3 species preferring this type of food in the lake. And so it seemed quite obvious to us that this was a peak. There must have been a peak in Eurycercus in the lake at this time. So that was the theory. It doesn't end there, because this guy, Stefán Stefánsson, who lived, he was born in 1854, and lived to 1929. He was one of those fishermen, and his father lived on the same farm. And in the late 1920s, when he was an old man, he wrote a report to this guy on the left side, Árni Einarsson, who was the leading fish biologist in Iceland at the time, or the only one actually, and asked him to publish it, and that's what he did, Árni. And in this report, he describes what fishing was in the whole of the 19th century in the lake. And you can actually, when you read his report, you can actually reconstruct the fishing quite in quite some detail. And this is his record. And now we have another peak that's the biggest peak of fishing ever in Myvatn for 200 years. And the peak year was in 1867, at least 150,000 fish. It could have been more, but that's the number that was given. So this number, we can use this number to actually calibrate the curves, the 20th century curve and the 19th century, so we can put them on the same level. So again, we have a new situation here. 1867 is the highest fishing record for Lake Myvatn ever. So it's a totally new situation to have this data. Or it's not a new situation because the historical data was always there, but we were not looking at it. So what we did the obvious thing, to take a sediment core from the lake, and we were able to locate a bay in the lake that had a high resolution sediment, where you could actually look at individual years, almost. And we also knew that you could look this guy here, this Eurocircus, has a carapace or a shell that preserves quite well in sediment, and you can actually extract it from the sediment and count them. So that's what we did. And we got this record. So this is a record that goes from 1975 and back to 1840. And the Eurocircus, the crustaceans, is almost matching the Arctic char quite well. So now we think we know what is determining the number of fish in the lake, or what was determining the number of fish in the lake in those days, before the fishing got modernized, which was very late. Around 1950, the fishing was modernized with motorized boats and new types of fishing nets. When you start taking sediment cores, you become addicted to that sort of thing. And so we kept going down into the lake, down into the sediment, down to the bottom of the sediment, and the whole 2,300 years. And the yellow guy here is the Eurocircus. This is the foot of the char and the ducks. And now you can see that the peak You can actually see the peak in the late 19th century. It's there. And it's an all-time peak. It's a maximum of the 2000 years. You can see the land now in the middle of the record, the settlement period. There's nothing strange happening at the landnam. Landnam apparently had very little effect on the lake, which is different from other lakes we have looked at, where the landnam has a big influence. And we can also see that the Eurocircus is related to what is, the green curve, the Eka-Gurupila curve, which is a green algae that is covering the bottom of the lake normally. And there's a mat of those algae on the lake bottom, and this mat of algae is very variable between years. And you can see this the record there. And we know that we've done experiments that show that the Eurocircus is favoring this type of algae as a habitat. The orange or light brown curve is Tanitarsus, which is the main insect in the lake, the main midge, or chironomid. And you can see that it has an opposite curve. It starts with a high density of midges and then downward trend to the present day. It looks like a Christmas tree. The bottom of the sediment is actually from a lake that was there before Lake Myvatn was formed. It's reworked sediment from a precursor lake. We'll come back to that later. Yeah, chapter 2. Coming back to this, this decline is the time we have spent working in the lake together with many other ecologists. And we were wondering if there was a balance, if there was overfishing, or if some recent mining operation was having an effect. So we were eager to see the results of the monitoring. We could hardly wait for the years to pass. The name Lake Myvatn, the Myvatn means actually midge lake, and it's famous for its huge populations of midges. And so this is a common scenery in the spring. The air is just thick with insects. The lake surface is covered with midges when they're emerging from the lake. They actually live as larvae on the lake bottom, and then in spring they emerge to mate. And there's another period of emergence in late July or early August. There are 2 generations for most of the species. There are about 30 species of midges. 7 of those are dominant, very abundant. And that's a creature. We have been concentrating on this particular species called Tanitarsus because it's the most abundant one, and it's a species that is so abundant that it can actually transform the habitat in the lake. It changes the bottom of the lake when the populations are high. When the insects are not in the air, they are at the bottom as larvae, and they are living in tubes. It's a The size is a bit exaggerated here, but just for illustration. The ducks dive from the lake surface down to the bottom, and they filter the larvae from the mud. They are filter feeders, like whales. They kind of filter the mud and get hold of the larvae. And the fish are doing more or less the same. They kind of filter their habitat to pick up the larvae from the bottom. We catch the flies as they emerge. We have traps on the lakeshore, all around the lake, and also along the river. And we count the flies and we identify them, and this is the type of record we have from 1976 to 2009. We are still doing this, and the scale here is logarithmic. So each step along the scale is a tenfold increase in the abundance of the flies. So in 1983, we found out that the midges were not stable at all. They were actually crossing from very high numbers to very, very low numbers. So the peak in 2000 is at the order of magnitude of 6.3, and the lowest is 3.4, something like that. These are logarithms, so these are enormous fluctuations. So the trap catches fluctuate from maybe 100 flies in the summer, it's a minimum, to millions of flies. The fluctuations, it took another fluctuation to realize that this might be oscillating, and it has been oscillating ever since, but not regularly. It's an irregular oscillation. And what we see in the lake is that the lake switches from a very good situation with a lot of midges, a lot of birds, a lot of bird chicks, a lot of flies, a lot of midges, a lot of diatoms, and a clear water lake. Sometimes you can see the bottom from the boat, and then the midge populations go down, and the lake changes color. It becomes green. Becomes opaque. You cannot see the bottom anymore. The char is not reproducing. The ducks do not produce any ducklings. The midges practically disappear, and the lake is full of small fish and cyanobacteria, which create this green color. And we kind of imagined that this was some kind of oscillations that were taking the lake from one situation to another. We would call it a regime shift. It's a concept that was just developing in the ecological literature at the time. It turns out to be more complex than that. We have a regime shift in the lake on a higher level. So the lake seems to be shifting between a stable situation and an oscillating situation. And these regime shifts are occurring quite frequently, and these situations are mixing. There's a mix of a stable situation and an oscillating situation that makes it very, very complicated. And it took some work to find this out, and it was done through mathematical modeling, and this was our moment of fame when this got published in Nature as a new way populations, wild populations, animal populations could actually develop over time. This was in 2008. So that was a breakthrough. And the current idea that we are kind of well, yeah, we're not quite sure if that holds, but it is still the working hypothesis. And that's when you have the midges covering the bottom, they actually oxygenate the bottom. They pump oxygen into the pipes and down into the sediment, which blocks the phosphate, and so the phosphate cannot dissolve from the sediment and go into the lake to drive the ecosystem. So when the midges disappear for some reason, this oxygen block or phosphate block doesn't exist anymore, and there's a lot of phosphate being released into the lake, creating an algal bloom, kind of eutrophication. So it's a eutrophication signal. It is apparently a natural thing. People are seeing this kind of pattern in many lakes all over the world. So that's a typical situation in a bad year. And so we started studying the bacteria, and now we are monitoring bacteria, both the seasonal pattern and in different years. And as you can see on the left-hand side, they are doing different things in different years. We cannot make any system of it, but there are more in midge-free years. You can see a histogram on the right-hand side showing the difference between years. We don't understand this pattern yet. It's not climate. It's no weather pattern in this. It's an internal system going on. And this is the lake during the clear water phase. So everything is clear and everybody is happy. And this has become a permanent situation now, together with the decline in the fish. In 1963, the bottom of at least the south basin of the lake was covered with these green algae, and now they have totally disappeared. And that seems to be a permanent and a long-term situation. So in summary, we have a long-term record. I mean, this is theoretical. It's not the record, but can imagine a long-term record in this hexagon. And it's a combination of many processes. One is climate, one is sedimentation. The lake is getting significantly more shallow. You have human activity at the time of settlement, and again in the industrial age. You have volcanic activity, mostly as tephra falls, which is episodic. You have soil erosion, which is episodic as well, and you have food web interactions, which is oscillating at around 7-year intervals. And all these different patterns, different influences are creating some sedimentary record of the biota. And to the ROCS project, the ROCS project was very exciting to learn about the project, and we tried to join as soon as possible because we could see the great advantage of having a DNA record of the whole thing, because we know a lot of things about Myvatn, and we would love to have a lot more things to work with. Not least the ducks, because the ducks do not leave other fossils than DNA. And so that's our hope that the ROCS project will do that. These courses were taken last winter, 1 year ago approximately, and the course have been analyzed and this is a preliminary record. The cores have been scanned, the samples have been taken, the diatoms have been analyzed. We've done the kind of preparatory overview of the bibliography. We're eagerly waiting for the ADNA record of this, and also the TEFRA record, which will fix the chronology, of course. And this is the core, and it turned out that half of the core is the recent lake. This is the lake that we are working with, and half of the core, the whole lower half of the core, is actually the sediment from the old lake, which is useless for our purpose. It's a sediment that has been baked by hot lava and has no organic material. So we are working with the upper half, and so we are eagerly waiting for the DNA record, and that was it. Thank you very much.
For more information about research at ROCS, visit our website at www.rocs.ku.dk.